Right, this video I'm going to try and focus on how students can move from a grade 8 to a grade 9. So the expectation here is that you know a huge amount of the content, and what I'm going to try and focus on is just looking at some key misconceptions students have, or often they miss out a few keywords, which in my opinion helps with moving from a grade 8 to a grade 9, and I'm going to focus on paper 2 AQA. Now, paper 2 start, the main content in paper 2 that's quite challenging is looking at equilibria. So first thing is defining dynamic equilibrium. So dynamic equilibrium is when you have a reversible reaction. So obviously you need to have a reversible reaction. So the most common reaction that we tend to see is where you've got nitrogen plus hydrogen that produces ammonia. You should be able to balance that. There's 2 nitrogens there, so 2 nitrogens on this side, 6 hydrogens, so 3 hydrogens on that side. So that's the reversible reaction. So you need a reversible reaction. Secondly, you need to have, you need a closed system. So you need to have a closed system, otherwise you will not reach dynamic equilibrium. And thirdly, the rate of the forward reaction equals the rate of the reverse reaction. So that's a really important definition. You have to remember to include the word rate. You can't just say the forward reaction equals to the reverse reaction. It's the rate of the forward reaction equals the rate of the reverse reaction. So that's what those 3 bits of information makes the reaction reach dynamic equilibrium. Often you might see a graph here where you've got a reactant, so you've got a certain amount of reactant, and as the reaction proceeds, that obviously the reactant concentration goes down, and then at the same time you will have product which you've got 0 to start off with, that will start to increase. Now because it's a reversible reaction, what will happen is some of the product will start to break down and reform the reactant, and therefore the concentration of the reactant will not continue going down, it will start to level off, and then the same will happen with the products, it will start to level off. Now they don't have to be touching, but the point of dynamic equilibrium is this. So this is the point at which dynamic equilibrium has been reached, and it may also appear that the reaction has stopped. So might appear the reaction has stopped. But actually what's just happened is, because the rate of the forward reaction equals to the rate of the reverse reaction, the reaction is still proceeding, but it has reached dynamic equilibrium. So that's the sort of the crucial bit around dynamic equilibrium. Now another part that I think students struggle with regards to dynamic equilibrium or reversible reaction is the Le Chatelier's principle. Now Le Chatelier's principle is an important principle, and what the principle suggests is that if there is a change in condition, so if there is a change in condition, equilibrium will shift to minimize that change. Okay, so the main thing we need to be aware of is temperature, pressure, pressure and concentration, or no, pressure, concentration, and catalyst. Now, those are your four variables that you can change, which will change the position of equilibrium. Okay. My advice is, when we're talking about temperature, you discuss endothermic or exothermic. When we're talking about pressure, you talk about number of molecules in either side, and avoid mixing these two. So pressure is exclusive to the number of molecules on either side, and temperature, you want to talk about endothermic, exothermic. Concentration, the main thing is just a change. So if concentration increases, equilibrium will shift to minimize that change, so it will try and decrease it. So there's nothing particular you need to talk about there. Catalyst has no effect on equilibrium. So you might say, well, why do we use it? The main thing is it speeds up both reactions. So speeds up both reactions. So the forward and the reverse reactions will happen faster. So that's a relatively straightforward one to include. They often put that in as a last question or a couple of marks. Concentration, like I said, it's mainly to do with changing. So increase concentration, equilibrium will reduce it. And then pressure and temperature, we'll talk about it now. Now, with temperature, the main thing you need to consider here is whether the reaction, which reaction is endothermic, which reaction is exothermic. Now, I'm just going to show just a reaction around, obviously nothing particular, it's just A plus B gives you C plus D. And we're going to say that the forward reaction, so this is known as the forward reaction. So that's the forward reaction, that is exothermic. Now, how you're going to see whether it's exothermic is if delta H is negative. So if delta H is negative, that means the forward reaction is exothermic, that means the reverse reaction is endothermic. So, and if you learn the understanding of one of them, you'll be able to reverse it for the other change. So increasing temperature. So if you increase temp, equilibrium will try and reduce it. So equilibrium will shift to reduce temp. Now, what can the equilibrium do to make the temperature go down? Now, we know that the forward reaction is exothermic, which means that the forward reaction will heat up the system, which means that the reverse reaction will cool the system down. So if the forward reaction increases temperature and reverse reaction decreases temperature, when you have increased the temperature, the equilibrium will shift to try and reduce the temperature. To reduce temperature, equilibrium will move to the reactant side. So to reduce temperature, equilibrium will move to the left. So it will move towards the reverse reaction, so it will move towards the reactant, because, so this is the explanation, because the reverse reaction is endothermic. So because the reverse reaction is endothermic, that is favored when you have increased the temperature, because the reverse reaction will reduce the temperature because the reverse reaction is endothermic. Now, if you learn the increase in temperature, you can then do this opposite for reducing the temperature. So if you reduce the temperature, equilibrium will shift to try and increase the temperature. Increasing temperature happens when there is more exothermic reaction, so therefore the Ford reaction is encouraged, so you'll get more products being produced because the Ford reaction is exothermic. And that's what the changes that happen when you change temperature. Now the other one is changing pressure. So when we're looking at the change in pressure, let's look at a different example. So say we've got A plus B gives you 3C plus D. Now again, this is just obviously a random equation. Now we will increase pressure. So increasing pressure, equilibrium will try and reduce it. So equilibrium will shift to reduce pressure. Now, in this case, I'm not going to talk about endothermic or exothermic. I'm just going to talk about the number of molecules on each side. So on the left-hand side, you've got 2 molecules. And on the right-hand side, you've got 4 molecules. So if the reaction goes to the forward direction, you get 2 molecules turning into 4 molecules. So that will increase pressure. Whereas if you have 4 molecules going down to 2 molecules, that reduces pressure. So if you've increased the pressure, the equilibrium will shift to try and reduce the pressure. The only way that you can reduce pressure is if the reverse reaction happens. So reverse reaction will reduce pressure because the left-hand side has less moles of gases. Okay, so that side has less moles of gases because 4 molecules become 2 molecules, so more of the reverse reaction will happen and that will reduce the pressure. And obviously when you reduce the pressure here, the equilibrium will shift to try and increase the pressure. In order to increase the pressure, the Ford reaction is encouraged because there's more moles of gases on the right hand side. Again, what I haven't talked about is endothermic or exothermic. I keep that exclusive for temperature. And when it comes to pressure, you talk about the number of molecules on either side and not mix them up. Don't use endothermic side or exothermic side. There aren't any endothermic or exothermic sides. There's directions, and that's it. You don't talk about the sides being endothermic or exothermic. So that's a common mistake students make. Right, so that's equilibria, and obviously there's a few other examples associated with this, but I'm not going to go through. I'm mainly focusing on how to push students from a grade 8 to grade 9. Okay, a couple of other things. Just on organic chemistry, so it's just going to be some random stuff that I think is where students tend to lose marks, or extension questions that they can ask you. Now, you need to know obviously alkanes and alkenes. In alkenes, you've got ethene, which is relatively straightforward. Propene, again, is also relatively straightforward. Remember, it's a carbon-carbon double bond between just a pair of carbons. It's not for all of the carbons. So that's ethene, that's propene, and then you've got butene. Now, with butene, there's a possibility that you can have 2 types of butene, and that's to do with the position of this carbon-carbon double bond. So this is called butene, but more specifically it's called but1ene. Now, you don't need to know the name, but they might ask you as an extended question if there is another possibility of butene. Now, if this is one possibility, and the second possibility, we call them isomers, is this structure here, where the carbon-carbon double bond has actually shifted from carbon 1 and 2 to carbon 2 and 3. So that's called but-2-ene. So these are very, very similar compounds, but slightly different. So we call these isomers. You won't need to know this until A levels, but sometimes if they think about extended questions, that's what they might ask for. Also, with the same theme of organic chemistry, this definition of a homologous series. So when something is in the same homologous series, what do we mean by that? The first thing is they've got the same functional group. So they will have the same functional group. So example would be, say, methanol. So say you've got methanol and ethanol. So these two are in the same functional group because they've got the OH group, and that's what makes them alcohol, so that's the same functional group. The other one is they'll have the same general formula. So what we mean by that is CnH2n plus 2, that's for alkanes, or CnH2n for alkenes. Okay, the last part of this is looking at, so you've got two substances, methane and ethane, and they're obviously in the same homologous series because they're both alkanes. Methane is CH4, ethane is C2H6. The difference between the two is CH2. Then you take propane, so that's C3H8. Again, the difference between those two is CH2. So what we say is when successive members differ by CH2. So that's the last thing that makes make two or more substances in the same homologous series, is when you line them up in order, the successive members will be different by the previous one by CH2. So that's what makes them part of the same homologous series. A couple of other things with organic chemistry. Just some alkene reactions. Now, the most common alkene reaction that you are expected to know for GCSE is, say you've got ethene and you react that with hydrogen, you'll end up with ethane. So you end up breaking the carbon-carbon double bond and attaching the two hydrogens on here. Alternative is if that H2 gets changed into something else, so say a halogen, say Br2, and again all that's happening is the carbon-carbon double bond is breaking and the two bromine atoms are just attaching onto the two carbons and the double bond's broken. Okay. The only other one that's slightly more tricky, or can be, is if you've got, again, ethene, but you're reacting it with water in the form of steam. What happens is the carbon-carbon double bond breaks again, the hydrogens shift like the others, but here you get a hydrogen and an OH splitting up, so you end up making ethanol. So that's one method of making ethanol, is the hydration of ethene, and this is how ethanol that is used in industries, in sanitization, that's how the ethanol is made, not the ethanol that people consume, because that is through the production of alcohol through fruits, so with using glucose. That's known as fermentation. So these reactions are useful to remember.